Hi guys, today's lesson is 2.11 on gravitational field strength on other planets. So let's review first the difference between little g and big G. So same letter, but a really big difference when we're looking at them. Little g has a vector on top of it. In the first unit, it was acceleration due to gravity, which is measured in meters per second meters per second squared. In this unit, we're calling it gravitational field strength and measuring it in newtons per kilogram. Those are the same units, just referencing different things. So vector quality, meaning direction, matters. And little g is different everywhere you go. So on the top of Mount Everest, little g is different than at the bottom of the Marianas Trench, as we discovered in the last lesson. Big G is the universal gravitational constant. It does not have a vector arrow, so it's a scalar. It's the same everywhere in the universe, and it's a constant on your formula sheet, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. In the last lesson, we watched a video that showed us using the Cavendish experiment how we calculate big G. So while big G is fixed throughout the universe, little g can change. This is similar to the idea of mass and weight, which some students are still struggling with. The mass of an object is the same no matter where it is in the universe. The mass is how much matter you're made up of. So I'm made up of the same amount of matter whether I'm on Earth or the moon, but my weight is very different on Earth than it is the moon. Since little g is bigger on Earth than it is the moon because of Earth's bigger mass, I have a higher weight when I'm on Earth than I do when I'm on the moon. This is confusing because we use the word weight in everyday English incorrectly. We use it to mean mass, but what we actually are talking about is the force of gravity when we say weight in physics. We can use this idea to determine some physics on different planets now. So this takes a little bit of adjusting because you're used to using 9.81 for acceleration due to gravity on Earth. But remember, that's an average at sea level, and it changes even on Earth. The acceleration due to gravity or the gravitational field strength can change depending on your altitude and even your latitude, as we'll see later. We're going to be referencing a data table on page 218 in the textbook. This tells you the mass and equatorial radius for different celestial bodies in our solar system. Your formula sheet has the information for Earth, but today we're going to be doing other planets and figuring out what the gravitational field strength is on those planets. So we'll need to use those planets' masses and radii. First example, how would you determine the weight of an object on another planet? Those of you struggling to understand the difference between weight and mass, I suggest that you highlight the word and always write Fg above weight because it is the force of gravity. Step 1, find the field strength on the planet. So let's say Venus for this example. And step 2, we'll use Newton's second law to determine the force of gravity or the weight. So using the formula, little g equals big G m over r squared, we're going to sub in the numbers we know. Here's big G, the universal constant. And now I need to find the mass of Venus. So I'm going to look on page 218 in the textbook, and I find Venus has 4.87 times 10 to the 24 kilograms. And I'm going to divide by the equatorial radius squared, which from the chart is 6.05 times 10 to the 6 meters squared. Pause the video, put this in your calculator, make sure that you can type it in properly. Now you should be getting a gravitational field strength of 8.87 newtons per kilogram. So on Venus, you will feel lighter. Your weight will feel lighter because G, the gravitational field strength, is less than the average we use on Earth, 9.81. Now we're going to use that number for G to figure out the weight. So remember weight, highlight it and write FG above it if you're struggling. Comes from the formula for FG on your formula sheet. Pause the video and find it. And it's really just Newton's second law, mass times acceleration, but we're using acceleration due to gravity. So you could write this as a W if you like, but I like to write it as FG. I'm going to put the mass of some random object, let's say 100 kilogram object. I'm going to put the G value, 8.87 on Venus, and the weight of 100 kilograms on Venus would be 887 newtons. You could put the direction in there because it is a vector. These are all going to be pointing towards the center of the planets, so towards the center of Venus. What is the gravitational field strength on the planet Jupiter? Pause the video, look on your formula sheet to find the formula, look in your textbook to find the mass and the radius, and see if you can get the same answer as me. There's your formula. Here's your substitution step. And you've got a gravitational field strength on the planet Jupiter of 24.8 newtons per kilogram, which is huge. Jupiter is the biggest planet in our solar system. It has the largest mass and the largest radius, so it also has the largest acceleration due to gravity or gravitational field strength. Try the next one on your own, pause the video, and come back to the solution. The gravitational field strength on Mercury now is the same formula, same substitution step. Different values for M and R for Mercury, 3.30 times 10 to the 23 kilograms is the mass of Mercury, and 2.44 times 10 to the 6 meters is the radius. This gives us a G value of 3.70 newtons per kilogram. I'm using those units because they asked for gravitational field strength. Even though it's the same as meters per second, this is talking about gravitational field strength, so I'm going to use the units that are appropriate. Oh, an announcement. It's like you guys are actually even in school right now. How exciting. So the field strength on Earth is also not fixed. It depends on two factors that I alluded to earlier, the altitude and the latitude. Altitude is how high above the surface of the Earth the object is placed. Altitude is in reference to the questions from last lesson on being at the top of Mount Everest or the bottom of the Marianas Trench. That's your altitude. How high or how much below sea level is the object that you're talking about. Latitude is a measure of north and south of the equator. So the equator is kind of that horizontal line that runs through the middle of the globe. And latitude is how far away from that line you are. So up here in Canada, we're quite a ways away from the equator. Some place like Ecuador, they're very close to the equator. This actually has an effect on your G value or your gravitational field strength. And the reason being is on the next slide. Although a globe that you look at in a classroom is a perfect sphere, The Earth is not actually a perfect sphere. It's something called a geoid that slightly bulges around the equator. So this shape is actually larger at the equator than it is at the poles. It kind of flattens out. So since it's larger, that means really you're higher above sea level than you actually would be if it was a perfect sphere. So the Earth is about 21 kilometers wider at the equator than it is at the poles. This is a picture showing the difference in altitude, so how high or low above sea level you are. And these imperfections might seem small. In fact, we've always just pretended they didn't exist in other conversations, but they do actually change the acceleration due to gravity or the gravitational field strength that you're calculating. And they can be worked into these formulas simply by subtracting the height of Everest or adding the depth of the Marianas Trench, for example. Reverse that. Subtracting the Marianas Trench, adding Mount Everest. Pardon me. So for this lesson, there's 3 questions in the textbook on page 229. Remember that you can use the chart in the textbook on page 218 to help you with these, and you can always email me if you have any questions. Good luck.